given a radius and a velocity. This one has to for how much time. The problem in the quiz gave you the time, so you can get the radius. Right? So it was exactly the same problem, worded in a very different way. So the concepts are not clear. Of course, if it's not identical, then you don't solve it, right? But that's not what you're supposed to do. You're supposed to understand what you're doing. So I haven't received the grades, but if you didn't get an A, I don't know what to say.
I heard like the average was like 35 out of 70.
Oh, you already? Oh, for what?
No, that was the test.
Oh, I don't remember what's that. Yeah, the test wasn't that great, right? But let's say, let me start now. Okay, so the first few weeks are shock, right? New subject, style, whatever. But this is, I think, at this point. If you have trouble, you are in trouble. For two reasons. Or either you're not studying, or you're really not understanding the concept, and you're not coming to me with questions. Or with anybody else. No, you don't have to be with me for questions, but you can go to tutors, you can go to other instructors. You should be getting good grades. Right? You have the tools. You have them. The other problem is exactly the same circuit we did in class. This is it from class. All right? The only difference is that the first part of the problem asks you to do Kirchhoff's, establish three equations. No, the junction rule, and two loops. And then it basically asks you what happens after a long time or just before it was just, these questions were part of part B, which you've already done. You had already done. You had to do a perfect quiz. A perfect quiz. Please, don't cry afterwards, okay? I'm available for you. The examples are there. You've worked them through. If you didn't get them through the class, ask me questions. This is the time. The exam is in 2 weeks. The next exam is the hardest.
Even harder than the final?
Yes, the final is actually not that hard. So it's hard, super hard, and maybe equally hard to the first one. So the second one is the hardest. Okay? All right. Sorry, I got upset. I'm going to put that word. I got upset. All right? All right, so now we're in chapter 29. I put the pre-lecture notes as well for the whole week. I was good this week. All right. Who wants to do well in the second exam? Good. Okay, well, there's some people that don't want to do well. What can I do? If you are having trouble, come to see me, okay? Sorry, I think you and I were going to be coughing throughout the semester, period. I'm just not cured. Okay, this chapter is called induced currents. So that's when I'm going to start the twisting of your brains. Okay, so that's why it's hard. Okay, we now know that a current can create a magnetic field, right? Michael Faraday, pretty famous name, famous physicist, thought there must be a natural symmetry, okay? That nature has some symmetry to it. That's what natural symmetry means. And that magnetic fields should also create currents, all right? So he devised this experiment, all right, where he created a current on this wire with a solenoid, all right? So he could create a magnetic field. Oh, you know what? Sorry, I just realized. Before we go into this, because of the solenoid, I realized that on Friday we didn't cover one thing. So sorry, pause, momentary pause, as we go over the last bit Where's chapter 28? There we go. All right. So this bit we didn't cover. Okay. I hope at home you solve this problem for part C. So reset. Okay, reset. We have to finish chapter 28, and then we're going to go through chapter 29. So we finished the class with applying all right, dear me. All right, where we found that the integral over a closed curtain, a closed contour of the magnetic field dot dl, where dl is the path, all right, dot being a dot product, is equal to mu 0 times the enclosed current. Sort of in the spirit of Gauss, but this is a contour integral, okay? And then we went to solve different problems, and one of these problems was given by this coaxial cable with a solid cable in the middle. And we solved part A, B, and D. And I left for you to try this one, all right? So I'm still going to let you try that one. You have to work a little bit, all right? And I'm happy to answer the questions. So remember that the first thing you have to do to calculate the enclosed current, obviously it will, for part 3, your contour will be somewhere within the coaxial cable. So the enclosed current will be the inner current that's going to the left, which we chose to be positive. But then part of the current will be enclosed by my contour that's going in the opposite direction. So the I enclosed for part 3 will be equal to I minus the integral of J, okay, of the coaxial cable from R equals B to an R where R is less than C but greater than B. All right? And this is an integral of an area, and this area is equal to 2 pi r dr. Okay? So that's what you have to do. Okay, the integral of b dot dA is simply b times 2 pi r, because it's a circumference and b and dl are parallel to each other. The negative sign corresponds to the fact that this one is going to the negative, in the negative direction. Okay? All right, so that's for you to work through at home. One sec. Okay, so now we're going to apply Ampere's law to a different configuration. Imagine we have a solenoid. A solenoid is a stack of rings, okay? A stack of rings. And in this case, because as with Gauss we need some symmetry, we'll assume a very long solenoid. So we're sitting right in the middle of, where we have to the right and to the left, hundreds and hundreds and hundreds of rings, all right? So that the magnetic field within where I am standing is basically uniform and horizontal, all right? I don't see these changing shapes going outward, okay? I'm so embedded in the solenoid, and the solenoid is so long, I don't see these lines turning on themselves. It's such a perfect solenoid, making a perfectly horizontal field inside of it. So I'm going to use Ampere's law to calculate the magnetic field inside of it. So you choose a path, all right, as this is showing. Now, you can put points C and D very far away. So this loop I've generated, this path, this closed path, can have very long, super long sides B, C, and AD. Imagine they go basically to infinity, okay? Bless you. And that's perfectly allowed. My contour can be that exaggerated. Alright, so now I integrate B dot dl on this closed path. Let's say that I start A. From A to B, alright, the path and B are parallel to each other, right? So B dot dl are parallel to each other, and for this case, alright, for this case, we have that this integral is equal to the integral from A to B of B dl, right? Because B and L are parallel to each other. I'm choosing that path to be in the direction of B inside. Then I go from B to C, right? I'm not even going to write it. From B to C, you can see that the path is perpendicular to B in this region, so that would be 0, all right? And no matter, even if I go out, the path, it becomes parallel in the opposite direction. So anywhere along BC, the magnetic field is perpendicular to my path, so that contribution to the integral is 0. CD is so far away at infinity, okay, that the B is basically 0, right? That's what that means. Therefore, that integral, B being 0, that piece of the integral is 0. From D to A, again, the magnetic field and the path is perpendicular to each other. So the contour integral, meaning the closed path integral of B dot dl on that contour that I drew, it's basically here. And that's it. So this is equal to B times a length L. L being equal to, all right, this, the distance, right, between A and B. All right, that's it. So what is it? But then what is the current enclosed? Well, the current enclosed would be a bunch of rings, upper rings, right, whose current is going in. How many? Well, let's call them N. Many, N. All right, so this would be equal to mu 0 N times I. All right? So therefore, what is the magnetic field? The magnetic field will be equal to mu 0 I N over L. N over L is sort of like a loop density, right? The number of loops per unit length if I turn that into a little n. So mu 0 I N, where n is now the density of loops per unit length. All right? So that's my magnetic field due to a solenoid. All right? Now we had already calculated this before, I think. All right? So that's our result. And I invite you to look at this slide in detail. All right? But we had done this by calculating using Biot-Savart's law of a single loop. What's the magnetic field at the center of a loop? All right? Of a single loop, and then multiply it by n if we stack many. So these two results appear to be different. So if you want to, so the way to do this, to connect those two results as being the same, I have to go back to the result we got for a loop at any position away from the center.
Bless you.
All right? So we had this result away from the center. When x becomes 0, meaning I'm at the center, I recover this result. All right? So away from the loop, centered, I get this result. So now that's the contribution of a loop, all right, at the, if I put a loop here, which is at a distance x from the center, call it 0, all right, its contribution of magnetic field to this point will be given by this expression, which is equivalent to having the loop in the center and asking what's the magnetic field at x. Okay, so this is the symmetry there. So I use that result, but then I integrate from minus infinity to infinity in the number of loops. Each one contributes, okay, a magnetic field given by this, where now the current is a differential current. Each one will contribute a current. How much current? Well, it's the density of loops times the current, right? That will give me the total current dx. It's like the ribbon problem. Remember the ribbon problem? Right? We had a stack of wires, so it's the same thing. All right? So you divide the width, which is n, divide by the length of your solenoid, times the current, dx gives you the current. Okay, so I replace that I by this term, and then integrate. So if you integrate, which I won't make you suffer and roll your eyes and go to sleep, but you suggest you go through this, you end up, after I do a lot of work on the integral, which we already did, because it's the loop one, and then you all of you rolled your eyes at that point, when I had so many substitutions. But here they are. I mean, I put them back here, and you get that B at the center of a stack of many, many, many loops, we recover the same expression that we had before. All right? So it's not inconsistent. We just have to go back to the original expression and re-express the current accordingly, and then we get the same expression as before. So, all right, so that's for the solenoid. There's another type of solenoid, the solenoid that's in the form of a toroid, okay? So you can make a toroid of loops surrounding like a nice donut. All right, let's say that we have a donut solenoid, okay? It's called a toroidal solenoid. So now if we apply Ampere's law to this configuration, you will see that, for example, for a path whose radius, right, I just crossed through the toroid in the middle. I slice it in the middle. So this is a slice right through it. So the wires in the inside will see the current going in, and the wires on the outside will see the current going out, right? So that's what this means. I crossed with an axe through that donut and identified that the wires were carrying current into the board inside and going out of the board outside. It doesn't matter. I could have had the other way around. All right? For this particular current, that's the case. Now I draw paths. I want to know what's the magnetic field in different places of this donut. Inside the donut, in the inner, what's it called, the donut hole, right? I want the donut hole region. I want the inside of the donut and then outside of the donut. For inside of the donut hole, I trace a path whose radius is r, but it's less than the inner radius of the solenoid. There, we anticipate the magnetic field, right? The solenoid, we said, a solenoid is just a simply stack of rings, right? And the magnetic field was horizontal inside of it. That's what we saw in the previous slide. If I just bend it over, all right, I expect the magnetic field to simply turn on itself and be circular, right? So if there's any magnetic field inside, it should sort of be either going clockwise or anti-clockwise. Let's say that I don't know right now, but let's say that perhaps it cannot be going in a crazy direction. It has to be sort of in that direction, right? Or clockwise or anti-clockwise. And so I took a path, but then I asked myself, what is the current enclosed by this path? What is the current enclosed by this path? How many wires are inside of this path? 0. So, what is the magnetic field? 0. Because the current enclosed is 0. All right? The integral of B dot dl is 2 pi r, which would be the circumference, times b, right? But it's 0 enclosed current. And because r is not 0, b must be 0, right? Now, if we go all the way to path 3, all right, path 3, that is outside the donut. Again, the magnetic field has to be sort of either clockwise or anti-clockwise, but somewhat parallel to the one sandwiched in the middle, right? In that case, why is the current enclosed?
0.
Sorry?
0.
0, exactly. Why?
Because there are no wires outside of the outer edge.
But what I want to know is how many wires are inside. So if I said yes, correct, what did I mean? then?
Then like the charges must be like going in different directions.
And then,
So like the net charge will be 0.
and in this case, it's not charge, it's current.
Oh, okay.
But okay, yes. So the total charge going out is the same as going in. So the total current enclosed by this contour is 0. All right, we don't care what's outside. We only care what's inside the contour. All right, that's very important. So the magnetic field, given that the path integral would give me B 2 pi r, right? 2 pi r is the circumference of that path. What would be the magnetic field magnitude if the total current enclosed is 0?
Wouldn't it also be 0?
Of course, it would be 0. Now the question is, what's inside the donut? What's the filling? What's the filling? So the filling, let's work on the filling. So this is, again, our Ampere's law, all right? As you can see, if I put a contour right in the middle, I only enclose half of the just current going into the board, right? I just enclose current into the board in the middle path. The one that's outside of it, I don't care for. I just care for the one inside my contour. And inside my contour, all the wires are going in. I have no wires going out. So the net current will be N times I. N being the number of loops that I've put in my contour. What is B dot dl? Well, that will be equal to, since dl is my path, and it's parallel to B, B dot dl is B times 2 pi r, as every one of those integrals. All right? Therefore, B, in this case, will depend on the radius. Mu 0 and I over 2 pi r. All right? So the closer you are to the inner part of the donut, the magnetic field is stronger than it is as you move away from the center. So in contrast to the magnetic field inside a solenoid that was all straight where the magnetic field was constant, mu 0 little n, where little n is a density of loops, now we have a bit of a dependence on the radius. Now typically in problems that we talk about, if we put a toroidal solenoid, we say that the radius is, the change in the radius is so small that you can consider the magnetic field to be constant. Okay, so the average radius would be the average magnetic field, and we can consider it to be constant. So we don't want to give you such a headache, but keep that in mind. All right, we try to help with some simplified versions of the problems. Anyways, okay? So these were examples where we use Ampere's law in a little bit different way from the geometry of the coaxial cable and the cable. These are standard problems, okay? These, the toroid and the solenoid, are standard results, okay, that we will use frequently. But the previous things that we saw on Friday, where we want to calculate the magnetic field due to a configuration of coaxial cables and cables, you have to work through Ampere's law and give us a value. Like we did with charges, right? Using Gauss's law. Now we turn to chapter 29. And the reason that I realized that we were missing chapter 29 is that Faraday was, of course, working with solenoids. Now we know what a solenoid, the magnetic field of a solenoid is, right? So the magnetic field, so we start a current, and we have a solenoid with many windings. We create a strong magnetic field through those rings, right? And so what he was trying to measure is that if a magnetic field is created due to a current, then without having a battery, just a wire with a winding, I should see the creation of some magnetic field here. Well, sorry, the magnetic field here should create a current, so he had an ammeter here. And nope, nothing moved. He had a strong magnetic field, and nothing moved. So being a, this is the sign of a great experimentalist, where they look at the details. No, they have this idea. There should be symmetry. There should be symmetry in nature. Why am I not getting it? So he tries, he couldn't get it. Meaning, he couldn't get it as he had magnetic field and he could never measure a current. And almost like a moment of desperation, he said, he turned it off, turned off the current, and he saw the needle move. So then he connected it back on, and he momentarily saw that current move, and then it stopped. Once the magnetic field was established, it stopped. He disconnected, and then the needle moved briefly, and when the current stopped, then finally this stopped really. So suddenly he realized that the symmetry came not in having a magnetic field, but while the magnetic field was building up, or while the magnetic field was dying out. That brief moment, okay? That brief moment when I connect the circuit and I go from zero magnetic field to a magnetic field, we go from zero to some magnetic field because that will be the current on the solenoid, there was a current created. But once the magnetic field was established, there was just nothing happening in this circuit. But when Faraday went from having magnetic field to no magnetic field, meaning he made the switch go off, okay, the magnetic field was established in the solenoid, and suddenly he took the switch off, so of course the magnetic field died, and over that brief moment of going from B to zero, this had a current. That was an amazing discovery, all right? So it was a momentary current that appeared when the switch was open or closed that really was incredible. So the magnetic field changing from zero to B or B to zero made the difference. So he then went to do another experiment where he had a permanent magnet, and indeed he moved the magnet in and out of the coil, and he could see the needle move. All right? Unfortunately, we're far, far away from our demo room, and it's not possible to show you, but it is so brief. If I were here with my demo and I would bring you a magnet, you would just see a needle move like tick, tick, tick. It's super brief, all right? But by me just moving that magnet up and down in a circuit that has nothing except me moving the magnetic field. So a changing magnetic field through those coils creates a current, okay? But of course, if I stop moving the magnet, there is no current. As soon as I move the magnet, then there's current. Okay? Again, if we don't have a current, and he could do the reverse. Okay, so he was doing the magnet, but then you can also have a permanent magnet and move the coil in and out of the magnetic field, right? You could do that symmetry too. And again, if he moves the wires, the circuit in and out of the magnetic field, he would see the needle, the ammeter needle move, but if it was stationary, then nothing happened, okay? So pushing the coil into the magnet or out of the magnet, it would move the needle. But also, he started to notice something important. If you push the coil into the magnet, cause the needle to move in one direction. If you move the coils out of the magnetic field, then the current induced on the current that the ammeter measured was in the opposite direction. So it was sensitive whether it was going in or it was going out, the direction of the current. So that was another observation. All right? So Faraday found that there is a current in a coil if and only if the magnetic field passing through the coil is changing. A current in a circuit which is produced by a changing magnetic field is called an induced current. The creation of an electric current by a changing magnetic field is called electromagnetic induction. Okay? This phenomena, electromagnetic induction, runs our economy. This is how important it is. All right? As you will see in the next couple of weeks. All right. So if there's a current induced, there must be an induced EMF, right? Because ultimately, if there's a current, you would say, well, what creates currents are batteries, right? Or some type of voltage. So there is an induced EMF as a result of this. So you already would imagine that that would be the case. So let's say that you have a piece of metal that you start moving it in a magnetic field. A piece of metal has electrons that are free they don't like their parents. Well, they do like their parents, but they want to be free particles, right? And the parents being the ion lattice of the metal. Now, well, in this case, let's assume that the positive charges are the ones that are moving because we have a current, say. All right, so my drawing has a proton, so obviously that's not what's happening. And so therefore, I move this bar in a magnetic field with velocity v, right? What's going to happen to that positive charge? On my, I should have put an electron, sorry. But anyway. Yes, bad name. Cross. But let's say this imaginary positive charge in this metal can move, all right? And therefore, it's in the metal. I move the metal with velocity v. What is the force? Is there a force on this thing? Sorry, I'm blocking you. I'm body blocking you. So, what is this? Is this correct? Would the charge move? Okay, maybe we should go to the physical world. Electrons, right? There's a metal with electrons. Forget about my drawing.
Yes, it does feel a force because there's a magnetic field and it's moving perpendicularly to it.
Exactly right. Thank you. Right, so there's the bar. There are electrons, right? I'm moving with velocity v, right? In a magnetic field that's pointing into the board. What's the direction of the force felt by this electron? What is the direction of the force felt by this electron? So, right, so we use our right hand, which I didn't see enough hands moving, all right, on the day of the quiz, but it's the velocity cross the magnetic field would give me the direction of the force if it was positive, but because it's negative, it's pointing in the opposite direction. So an electron would feel a force going down, which is equivalent to a positive charge feeling a force going up, right? So that's what this drawing is about. And so electrons will start to accumulate down here, right? Meaning there will be positive charges on this side, right? Right? So by moving this metal, I created a separation of charge, all right? And the electric field and the force between them, all right? How much charge will I accumulate up to where it balances out the magnetic force, right? Electrons will move down until they feel a force of attraction due to the electric field, right? So as soon as charge separate, charge ones, they want to get back together. Positive and negative, if you stop moving, if there's stop motion, the electrons will go back and all this will become equally distributed, right? But because I'm moving this bar, electrons will feel a magnetic force, and while that magnetic force is stronger than the electric force, they will continue to accumulate up to where the two equilibrate, right? So the electric field force will be equal to the magnetic field force, and that would be sort of like the state at which it's going to finally stay as long as I'm moving that bar at constant velocity. Okay, so the magnetic force separates the charges in a moving conductor, which creates an electric field inside the conductor with strength equal to the velocity times the magnetic field, right? As long as the velocity is perpendicular to the magnetic field, all right? All right, but that basically creates a difference in potential, right? Given by the length of the wire. So the electric field is D, velocity times the magnetic field. L is the wire length. So that would be, right, the voltage across that wire. All right? The potential difference depends on the strength of the magnetic field and the wire speed through the field. And that generates an induced voltage that we call the induced motional EMF. It's motional because it needs to move to be able to be created. all right, of a conductor moving perpendicular to magnetic field, and it's given by this. So that voltage created by the movement of a conductor, all right, creates a magnetic, a separation of charges, which is basically creating a voltage across that wire and creating an EMF, all right? And now let's say that I connect, so I connected this conductor, right? I'm moving it, but so charges are now separated. What would happen if I connect a wire across like this? Now I choose a wire to close the circuit. What will happen? There will be a current. All right? There will be a current. So indeed, they cannot go this way because they're being separated by the magnetic force, but if I connect them some other way, the current will go through and cancel the charges on this side. And if I continue to move, it will be like a battery. The magnetic force will continue to separate the charges. The current will still continue to cancel it, like a battery. Do you see it? All right, let's see. So yes, we have a battery that's chemically separate charges, and the charges cannot get together in a battery because the chemistry of the battery is impeding that. But if you connect it into a wire, it will create a current to do that. Of course, the chemistry will again separate them, right? It will continue to, so let's say that the convention is that positive charges are the ones that have the current, so the positive comes back down and it's supposed to be negative. Well, the chemistry will immediately make it move up again, hence it will up, right? Up the ladder of potential energy. The same will happen here. If I move positive charges here and they end up on this side because of I'm moving this bar, the magnetic force will force it to go up, all right? In the same way as a chemical battery. So here is an example problem, and we'll leave it like that. This is the example problem we're going to solve. All right? Consider two rods sliding on a rail at a constant speed. Okay? The two rods are A and B. All right? They're not simultaneously on the same rail. All right? And they are traveling at a speed of 3 meters per second. Okay? Where in both cases the magnetic field is 0 in one region and has a strength of 2 Tesla. Of 2 Tesla in another. Okay, so you see one has a vertical magnetic field, this one has a horizontal magnetic field. Okay? Compute the magnitude of the EMF induced in the rod that's moving, okay? And determine which end is positive. Go. You have a good 5 minutes. All right, remember the conductor is like the piece of metal we just discussed. It's moving at a velocity v, right? Electrons are the ones that move, but convention tells you that the current is going in the opposite direction as the positive charges are moving. Is the velocity the same for both bars? Yes, I see a nod coming. Is the magnetic field intensity the same in both? What about L? L is different. Why is L different? It's not zero. No, there's a region where there's zero magnetic field, but the bar is in a region where there is magnetic field. Yes, where is it? I don't. What? The unit will be what? 0.4. 6 times. Give me the number. 2. I should have grabbed my glasses. I am in denial of my age. Please. Yes. Yes. Correct. I see a correct. Perfect. But it's in centimeters. All right. So I saw two guys in the back that had the right answer. Let me see over here. Okay, halfway through. Not there yet. Not there yet. My glasses. Dear me. I can't read this. 15 and 42? I think not. But you're close. Warm. Warm. Of course. Yeah, you got it. Okay. So with this, right? So in the first case, the magnetic field is the same, the velocity is the same, but the length that is in the magnetic field, in one case is the full 7 centimeters, and in the second case, only 5 centimeters is in the magnetic field. The contribution on the top doesn't count because B is equal to 0 in that region. All right? Is that where my pre-lecture notes end? Or do we have more problems there? But I guess we don't have time in any case. But okay, I will cover them on Wednesday. All right? Have a good rest. Oh, I have office hours right now?
Your glasses are on your head.
Oh, thank you very much. Oh my God. Thank you so much. I have office hours right now, all right, from 10:30.